In a previous video, we gave an overview of the light-dependent reactions, which are essentially occurring across the within or across the thylakoid membranes, right? And that we zoomed in on one and we saw, okay, we have some energy from light exciting the electrons within that chlorophyll pair, that P680 chlorophyll A pair. That electron, that energized electron, will then be transferred from one molecule to another, and as it does so, it'll go to lower and lower energy states, and that released energy, some of it will be used to transfer hydrogen protons across the membrane, and then eventually that electron will make its way to photosystem 1, where it can get excited again. If we think of it as the same electron, it doesn't necessarily have to be the exact same electron. But we can think of that same electron as being excited again by light energy, and then it can once again go to lower and lower energy states, and this time it's going to be used to reduce NADP plus to NADPH. Now, NADPH itself is an input into the Calvin cycle, but ATP is another input we need for the Calvin cycle. And the way that we produce ATP is that hydrogen ion concentration that increases on the inside due to it being essentially pumped across the membrane, as well as the leftover hydrogen ions from the water after it's stripped of electrons to replace that originally excited electron in that P680 chlorophyll pair. Well, that increased hydrogen ion concentration can be used to drive ATP synthase, which creates ATP from phosphate and ADP. And we saw that over here without seeing the different components. You get light, excite the electron. The electron goes to lower and lower energy states. As it does so, as it's going from photosystem 2 to photosystem 1, some of that energy is being used to pump hydrogen ions into the thylakoid lumen. Then the electron can get excited again. And then as it gets transferred and goes to lower and lower energy states, it can be used to produce NADPH, where, once again, its electrons are still at a fairly high energy state, so it's a strong reducing agent, and so that's why it's valuable in the Calvin cycle. That energy from acting as a strong reducing agent can be used to or help in the creation or the eventual creation of the sugar. And once again, where does that electron, once it gives it away, how does it get replaced? Well, it snags it from the water. What I have here is a more detailed diagram that labels some of the actors. And the important thing is really what we just covered and what we covered in more detail in the previous video, the conceptual idea of what's happening in the light-dependent reactions. But a lot of times in your biology class or in your biology book, you'll see talk of things like a cytochrome complex and plastoquinone and things like that. And I want to look at that right now so that you're not intimidated when you see it and that you see that these are just the actors that we talked about. So right over here, this is photosystem 2, and what you have, and I give credit for where this image comes from, it's modified from the light-dependent reactions of photosynthesis figure 8 by OpenStax College. But this right over here, we see the light is interacting the way it's depicted here, not directly with the chlorophyll pair within photosystem 2, that P680 chlorophyll A pair. We see it acting on some of these neighboring molecules. As their electrons get excited and then go to lower energy levels, that energy can be used to excite neighboring electrons. This kind of keeps happening. That energy gets transferred eventually to excite the electron in that P60A pair. And then that electron, it's the first electron acceptor, you'll see this sometimes is spoken of in your biology textbooks, is pheophytin. And then that can then transfer the electron to plastoquinone. And that plastoquinone is interacting in this cytochrome complex, which transfers the electron from plastoquinone to plastocyanin. And as it's doing it, you see the hydrogen ions being transferred from the outside of the thylakoid to the inside of the thylakoid, which is exactly what we've been talking about. And then as we go to photosystem 1, well, that electron can be transferred from the plastocyanin to the chlorophyll pair, the P700 chlorophyll. That can get excited again. Once again, it doesn't have to be the light directly exciting it. It can be exciting other molecules within the photosystem, within photosystem 1, but that energy eventually gets transferred to that chlorophyll, excites its electrons, and then it goes from one molecule to another, eventually goes to ferredoxin, which is being used in conjunction. It's one of the actors that the enzyme NADP plus reductase needs, along with NADP plus. So it's essentially just reducing NADP plus along with this electron that's on the ferredoxin to produce NADPH. And once again, what's going on here? Well, this is the ATP synthase that is using all this increased hydrogen ion concentration on the inside of the thylakoid to pump or to power you could say the motor, or that the ATP synthase is the motor that is powered as these hydrogen ions go down their concentration gradient. And that energy is used to jam the phosphate onto the ADP to produce ATP. So I've said essentially the same thing 2 or 3 times already in the last 2 or 3 videos, but I'm doing it because when you first see this, it seems very, very intimidating and very, very complex, and it is complex. And frankly, it's amazing that things like this are happening on the plant that I'm looking at outside of my window right now. And it kind of boggles my mind that this kind of thing is happening in nature. And there are bits and pieces of it that aren't fully understood yet and still need to be discovered. But at the same time, the general idea is not as intimidating as these diagrams appear. So hopefully you find this awe-inspiring like I do, and not as intimidating as what some of these words might make you feel initially.